Okay, so MATLAB, as I said, has very different algorithms for solving different matrices. But all these algorithms are basically like that. You may not be doing LU decomposition. You may be doing something called a Cholesky decomposition, for example. That works extremely well for symmetric and positive definite matrices. But the Cholesky decomposition is also an n-cubed algorithm. The constant in the n-cubed may be smaller to take advantage of the symmetry of the matrix, but it's still an n-cubed algorithm. And if you solve it with multiple right-hand side, it'll still basically cost you the same. Right? So there are many algorithms that can do AX equal to B for you. You can do QR decomposition, singular value decomposition. They are all n-cubed algorithms. So what does that mean to our partial differential equations? Well, the implication is if you look at the partial differential equation, in the most general case, if we have n grid points, that's infinite difference, or cells, or control volumes. Cells, it's also called control volumes. That's infinite difference, or basis functions. That's infinite element, right? So if you have n basically degree of freedoms, my cost is about n cubed. So this is actually a lot worse than what looks on paper. For example, when you look at a three-dimensional problem, right? I want to solve fluid dynamics in this room, and the question is, how does the cost scale with my size of the discretization? So for example, let's give an example. If in 3D delta x is equal to delta y equal to delta z, no matter if it's the size of a grid point or control volume or element, if you're doing finite element. So my n is going to be 1 over delta x cubed, right? Because has to be that many cells to fill the three-dimensional space. My cost is going to be 1 over delta x to the 9th. Okay? That's horrible, because if, for example, I have second-order accuracy, okay, and I want to get one more digit of accuracy out of my solution, that means I have to decrease delta x, delta y, delta z by about a factor of 3, right? 3 squared is about 10, so I need to decrease every direction by a factor of 3. So the number of degree freedom gets increased by something like 27, and the cost is going to be increased by something like, I don't know how much, 27 cubed. So that's actually not really a sustainable solution. Okay, I'd like to point out a little bit that MATLAB also has algorithms that actually looks into the sparsity of the matrix. So that is actually particularly helpful if your grid points are structured, right? So if you have a completely unstructured mesh, sometimes it can actually cost approximately that much. But for example, if you are solving a one-dimensional problem and your matrix is actually banded, right? As we see, we get a tridiagonal matrix out of finite difference, finite volume, or finite element. So MATLAB actually looks into that and uses a banded matrix algorithm to solve for that. So the cost is actually quite less than that, particularly if you're in one dimensions. In 2 dimensions and 3 dimensions, even if you have structured mesh, it's actually getting close to 1 to the delta x to the 9th. And if you have unstructured mesh in 2 or 3D, then it's pretty much like that. Maybe 1 over delta x to the 8th or something, but not much different. All right. So this is the motivation for having a better way of solving large linear systems like that. Okay, something that does not scale to the cube of the dimension. Okay, so what's that algorithm? So, I mean, nothing comes for free. So the way you solve this algorithm, solve this matrix system faster, is by exploiting the sparsity of the linear system. So what does it mean by sparsity? Sparsity means if you look at a matrix, most of the entries are 0. Okay, I mean, and this is actually why we are talking about solving linear systems with iterative methods at this point, instead of after learning about the fourth method of solving differential equations. Because the fourth method, the boundary element method, actually gets you a full matrix, not a sparse matrix. Okay, so there are ways to deal with that. You're going to learn in the boundary element methods, but like the sparse linear system method really applies most successfully in finite difference, finite volume, and finite element. Okay, so for example, when we are solving Poisson's equation in finite difference, we get a matrix like that. We get a matrix that is 2 over delta x squared minus 1 over delta x squared minus 1 over delta x squared, and then it just goes on like this. The sparsity of the system, which can be quantified by how many non-zeros there are in the matrix, divided by how many total entries there are in the matrix, actually gets smaller and smaller as you increase the number of grid points, right? So there are actually less than 3 times n non-zero entries, right? So if, non-zero entries, I think actually exactly 3n minus 2, right? And n squared total entries. So sparsity is basically going to be less than 3 over n. So as you increase n, the system gets sparser and sparser and sparser. So that's what we are taking advantage of. All right. And for example, one of the most efficient, one of the easiest way to take advantage of the sparsity of the linear system is what we call MATVEC, matrix vector multiplication. So if you, instead of solving ax equal to b, what if you just want to compute y equal to ax? Well, if you don't take advantage of sparsity, how many operations do you have to do? N squared, right? You have basically traversed every entry of the matrix. But if you do take advantage of the sparsity, it's an order n operation, right? Basically, if you know in advance where are the entries that are non-zero, you only have to go through these entries, and therefore you get a great speed up, especially when n is large. This is actually exactly the same for finite difference, finite volume, finite element, as you go to 2D, 3D, and arbitrary dimensions. Because whatever dimension you are, every grid or volume or element has a fixed small number of neighbors, right? So if you do finite volume in 3D, for example, every cell, if it's a structured mesh, every cell has a neighbor upward, lower, left, right, front, back. So 6 neighbors. And if you do finite element, it's a little bit more because every basis function centered at each grid point has overlaps on all its neighboring 8, right? The neighboring 8 elements, but each element has multiple basis functions that are non-zero. So at the end, you have about 27, actually 26, right? So you have 26 non-zero entries in each row of your matrix, right? So a little bit more than that, but like it's going to be a finite number independent of what n is, how many total non-zero entries there are. Okay, so basically sparsity of the linear system is a great thing to take advantage. And we know how to take advantage of that when we are computing y equal to ax.